Whether the light is a particle or a wave, the debate on this topic first began in the 17th century. Newton was convinced from different interpretations of the experimental evidences that light was a particle. Huygens, on the other hand, said that light is a wave. According to Newton's corpuscular theory, every source of light, like the sun or a candle, emit large number of particles called corpuscles in a medium surrounding the source. These corpuscles travel in straight lines with high velocity in all possible directions. When these particles enter our eyes, an image of the object or sensation of vision is produced. Huygens' principle states that every point on a wavefront, see this plane wave, every point, these circular red dots on a wavefront give rise to secondary wavelets, these small waves, which spread out in all the directions with the speed of a wave. The new position of the wavefront at time t can be determined using Huygens' principle. This new wavefront is formed by drawing a line tangent to all the wavelets. This line is tangent to all the wavelets. This wave-particle debate of light was resolved by famous physicist Thomas Young's double-slit experiment. On the basis of interference pattern observed on the screen in this experiment, Young arrived at a judgment that light must be a wave, as interference is a property of waves. Broglie's question was, if photons exhibit wave and particle properties, would all matter do so as well? De Broglie postulated the wave nature of electrons. Einstein appreciated his brilliant idea. De Broglie's theory was proved to be correct after Davison and Germer performed the double-slit experiment in 1927 using electrons. An interference pattern was observed by the reflected electrons. Hence, de Broglie's theory of matter having wave properties proved to be correct. He associated waves with matter because electron is a particle, material particle. Due to his revolutionary findings, de Broglie won the Nobel Prize in Physics in 1929. His work marked the beginning of the development of wave mechanics. As we have studied that electron diffraction is an evidence for wave nature of particles, we can reproduce the results of Davison and Germer in laboratory as well using the electron tube. So this is an electron tube in which the electrons from the heated filament are accelerated to high speeds by the large potential difference between the negative terminal cathode and positive terminal anode. Now these accelerated electron beam passes through a thin sample of polycrystalline graphite. It is made up of many tiny crystals like this, each of which consists of large number of carbon atoms arranged in uniform atomic layers. The electrons emerge from the graphite film and produce diffraction rings on the phosphor screen. This fluorescent screen is phosphor screen. Now, these diffraction rings produced are similar to those produced by light, a wave passing through a small circular hole. The electrons are diffracted by the carbon atoms and the spacing between the layers of carbon atoms. The atomic layers of carbon behave like a diffraction grating with many slits. The electrons show diffraction effects because their de Broglie wavelength lambda is similar to the spacing between the atomic layers. Now in this experiment, it's worth mentioning that the phosphor screen, this fluorescent screen, also gives a flash of light for each electrons that hits it. These flashes build up to give the diffraction pattern. De Broglie's wavelength. Consider a particle of mass m moving with velocity v. De Broglie's Consider de Broglie's wavelength. Suppose a particle of mass m is moving with a velocity, then de Broglie's wavelength is given by lambda equal to h over mv. We have studied earlier for photons, we use Planck's equation, which is E is equal to h nu. For the wave behavior of subatomic particles like electrons, we always use de Broglie wavelength, where lambda is equal to h over mv. H is Planck's constant, v is the velocity of the particle, m is the relativistic mass, and lambda will be measured in meters. According to Einstein's mass energy equation, E is equal to mc square, as these two equations have energy on the left hand side, so we will equate right hand sides. H nu will be equal to mc square, or mc will be equal to h nu over c. Now, according to famous wave equation, c is equal to nu lambda, where nu is the frequency of incident photons. Please do not confuse this letter nu with v. V is the velocity of the particle, nu is the frequency of the photons. So we will replace nu over c by 1 over lambda according to this equation. So mc will be equal to h over lambda. As mc is the product of mass and velocity, it will be denoted by momentum and letter p, h over lambda. Therefore, lambda will be equal to h over p. Now, in order to find out the units in which lambda will be measured, we will again look at this equation. Lambda is equal to h over p. H is Planck's constant. Its value is 6.63 into 10 raised to the power minus 34 joules into seconds. So h is measured in joules into seconds, divided by mass is product of momentum is product of mass and velocity. Mass is measured in kilograms and velocity in meters per second. As 1 joule is equal to 1 Newton into meter, therefore we will replace J with N into M times S divided by kilogram into meter per second. Again, 1 Newton is equal to 1 kilogram meter per second square into M into S divided by kilogram into meter per second. This mm will be cancelled out, kilogram will be cancelled out, so lambda is left with m s minus 2. Again, when this s minus 1 is moved up, its power become positive, so 1 plus 1 will be 2, so s minus 2 and s plus 2 will also be cancelled out, so units of lambda will be in meters. Now, this de Broglie equation applies to all matter, anything that has mass, even to people. Now, we will see an example and come to know why we do not notice wave behavior in people. Suppose a person whose weight is 70 kg, m is 70 kg. It is moving at a speed of 2.5 meters per second. These are arbitrary values, just we suppose. And it's running at a speed of 2.5 meter per second through an opening of width 0.90 meter. Now, for diffraction to take place, this is the basic condition of diffraction, that width of opening should be comparable with the wavelength of incident wave. Now, we will apply de Broglie's equation. Lambda is equal to h over mv. Again, h will be 6.63 into 10 raised to the power minus 34 divided by m is 70 kg into 2.5. After calculations, this lambda comes out to be about 0.04 into 10 raised to the power minus 34. So lambda is of the order of 10 raised to the power minus 34 meters, which is far less than this width of opening. This is the reason that no diffraction effects would be observed, as this lambda is very, very small as compared with the width of the gap. People cannot be diffracted through everyday gaps. Hence, wave model is not used to describe the behavior of people. People are regarded as large particles. The Planck's constant h is the same that appears in the equation E equal to h nu for the energy of a photon. It is fascinating how the Planck's constant h is entangled or interlinked with the behavior of both matter as waves, that is of electrons, and electromagnetic waves as particles, that is photons. Now de Broglie's concept interprets electron in Bohr's model as standing waves. De Broglie realized that the electrons orbiting the nucleus is considered as a circular standing wave in this way that consists of an integral number of wavelengths fitting exactly within the orbit. See these waves. So electrons are considered as standing waves, circular standing waves. Therefore, their wavelength lambda will be equal to 2 pi r over n. 2 pi r is the circumference of the circle and n is the shell number. Like n is 3, n is 4. As we move away from the nucleus, shell number increases. This means that the angular momentum of each electron is quantized, as Niels Bohr postulated the electron as being a particle that orbits the nucleus in quantized orbits. The answer of the question what keeps electrons in their orbits is based on stationary wave ideas that can predict the spectra of atoms accurately. Now, as electrons are more massive than photons, they have smaller wavelength, and this is why electron microscopes have a better resolution than microscopes that use light. Diffraction of particle has many uses, like to find the structure of matter, the arrangement of atoms in metals and other materials using diffraction of slow-moving electrons, and to find out the spacing between them as well, and the structure of complex molecules such as DNAs. High-speed electrons from particle accelerators have been used to determine the diameter of atomic nuclei and to investigate the internal structure of the nucleus. Diffraction is a wave phenomenon that describes bending of waves around obstacles or openings and spreading out when traveling through small slits or apertures. I have discussed this topic earlier as well when we studied wave mechanics for ASLevel and quantum mechanics for ALevel students under wave-particle duality, starting from debate of Newton versus Huygens in 17th century till the development of wave mechanics in the year 1927. Today's lecture will exclusively discuss diffraction phenomena in further detail. As a reference, I have placed links of my 2 previous lectures in the description below. We will also compare different intensity distribution curves obtained using 2 or more than 2 slits, and will also differentiate between 2 different kinds of diffraction, that is Fresnel and Fraunhofer diffraction. As I have defined just now, that bending of waves around obstacles and spreading out when traveling through small slits or aperture is known as diffraction. Now consider these incoming wave fronts. Blue lines are wave crests and the gap between 2 consecutive blue lines is indicating wave trough. So after passing through small holes, what happens? Diffraction takes place, direction changes, and we get the diffraction pattern of the incoming wave fronts. Now, diffraction has a lot of applications. The expanding profile of a laser beam, the beam shape of a radar antenna, and the field of view of an ultrasonic transducer are analyzed using diffraction equations. Moreover, as physical objects have wave-like properties, diffraction of matter also occurs and is studied using the principle of quantum mechanics. Huygens principle of diffraction of light. According to Huygens principle, every point on a given wavefront, see this plane wave, every point which is labeled as red circular dot, it behaves like a source of light, okay, and it gives rise to secondary wavelets, these small circular waves, which spread out in all the directions with the speed of a wave. The new position of the wavefront is determined using Huygens principle. This new wavefront is drawn by drawing a line tangent to all the wavelets. See, this line is tangent to all the wavelets. And you must compare these two interference effects using different light sources. Even we use laser light, the interference pattern obtained is same. Okay. condition for diffraction. There is a condition for diffraction to take place, that size of the slit should be comparable with the wavelength of incident waves. Consider these two diagrams. In the first case, this opening is large, so diffraction effects are very minimal, okay? Because the condition is not being fulfilled here, because width of the gap is very large as compared to the wavelength of the incident wave. Now in the second case, the width of the opening is comparable with the wavelength of the incident wave, so diffraction effects produced here are more significant. Now, examples of diffraction of different kinds of waves. Diffraction occurs with all kinds of waves, including sound waves, water waves, and electromagnetic waves such as visible light, X-rays, and radio waves. Now this first picture shows water wave diffraction through a small hole in the dam, or small opening in the dam. Here you must recall ripple tank experiment performed in the laboratory, okay, which IGCSE and ASLevel students they perform in the laboratory to observe water wave diffraction. And this picture is that of sound wave diffraction through a crack on the wall. And this is the example of light diffraction, which is explained on the basis of Newton's principle that I have stated just now. Now another example of diffraction of sound waves. Sound waves in the audible range have wavelength from a few millimeters to a few meters. Sound waves diffract as they pass through doorways, and hence a noise in one room spreads out in the next room. This is because width of a doorway is comparable to the wavelength of a sound. That is, condition of diffraction is fulfilled here. So this is the reason that sound waves are diffracted. Now these are intensity distribution curves due to single slit and multiple slits. This is due to single slit. In case of double slit, this pattern is obtained. In case of 3 slits, this one. And in case of 5 slits, this pattern is obtained. So it can be seen here that maxima in case of multiple slits are of rapidly falling intensity, and they are well defined as well, as the number of slits increase as compared to the pattern obtained due to diffraction through a single slit. Now diffraction of waves using different light sources. Now here again in these two pictures, this picture is that of diffraction of coherent laser light. See, intensity distribution, maxima of equal intensity are observed. Now this is the sunlight, and after passing through the single slit, again the diffracted light passes through 2 slits, and we obtain alternate bright and dark bands. That is, after diffraction, interference takes place, and we get, due to constructive and destructive interference, bright and dark bands alternately, and bright fringes are all equally bright if slit widths are of negligible size. And central fringe, which is known as central maxima, will be white as path difference is 0 and all overlap there. That means the path difference, the path traveled by these two waves will be same if the slit widths are negligible. This distance d is close to 0. It means then the equation for the path difference, which is d sine theta, equals n lambda for constructive interference and n plus half lambda for destructive interference. In that case, if theta is 0, sine 0 will be 0. So all the wavelengths will overlap here in the middle, and we will get a central maximum fringe which will be white because all the wavelengths will merge together. Now diffraction of waves using different light sources. So you must compare the interference effects observed after diffraction has taken place in case of different light sources. This is the diffraction pattern seen using coherent laser light. This is in case of sunlight, and when we use light source like bulb. So it must be noticed that we observe the same pattern, that is alternate bright and dark bands respectively. Now here it's indicated that at central maxima we get a bright fringe where path difference is 0 because all the waves merge together. There is no extra length covered by the different waves. And to calculate first order, second order maxima or minima, we use these equations which we have studied in detail when we were doing interference. So for constructive interference, we use d sine theta is m lambda, and for destructive interference, d sine theta is equal to m plus half lambda, where m is an integer. We can write any letter here that indicates an integer, where m is an integer, 0, plus minus 1, plus minus 2, and so on. For first order, we substitute m is 1. For second order, we substitute m is 2 in both cases, and we get these values. Negative sign indicates that maxima and minima lie on both sides of the central maximum in the screen. Another example of diffraction. In fact, you have studied diffraction grating as well earlier, and the closely spaced tracks on a CD or DVD, they act as a diffraction grating to form the striking pattern seen when looking at the disc. Now, there are two kinds of diffractions, Fresnel and Fraunhofer diffraction. So I will try to explain the difference between these two kinds of diffractions. In Fresnel diffraction, source and screen are not far away from each other. Incident wavefronts are spherical, wavefronts leaving the obstacles are also spherical, and no convex lens is needed to converge the spherical wavefronts. Whereas in case of Fraunhofer diffraction, source and the screen are far away from each other. Incident wavefronts on the diffracting obstacle are plane. Diffracting obstacle give rise to wavefronts which are also plane. Plane diffracting wavefronts are converged by means of a convex lens to produce diffraction pattern. So just to recap once more, it's in fact a diffraction phenomena with key points. So the point source with wave ray and wavefronts, see the incoming wavefronts, these are parallel waves. After passing through the aperture, we get spherical waves spreading out in all the directions. This diagram shows that central fringe is having maximum brightness, therefore intensity is maximum in the middle. For other orders, first order, second order, on both sides, we get maxima of rapidly falling intensity. Okay. What is the reason here? Why we get maximum brightness fringe in the middle? Because all the wavelengths merge together and yield one color only. Okay. So theta is 0, so path difference is 0. Explained in this way that after passing through this gap, all the waves have same wavelength and they are parallel, and angle, this is angle. Okay. Earlier we studied in terms of theta, here it is denoted by t. So t is 0 in the middle. In fact, we can use any letter or any arbitrary symbol, but the equation is the same to calculate the path difference between two consecutive waves for constructive or destructive interference. Of course, after diffraction has taken place. So that d sine theta is here, a sine t. It is same. T is theta and a is actually the separation of slit. So in the middle, all the wavelengths, they merge together and all the colors they combine. Okay, there is no path difference, no extra distance covered by one wave as compared to the other. So the center will be having the maximum brightness. Okay, in this, so this diagram shows that angle T has some value. Okay, this is the angle between the central line and the wave which gives rise to first order minimum. Okay, we will use the same equation, d sine theta is equal to m lambda in case of destructive interference, or in this case we use m plus half lambda. Okay, where m is an integer. In this case m will be equal to 1. Okay, thank you for watching. Interference is explained when we consider wave aspect of light and all the matter. Therefore, this phenomena not only accounts for light waves only, but sound waves, water waves, infrared and microwaves also exhibit interference effects. Interference effects are not observed all the time, as the effect takes place only when the sources have a constant phase difference, same frequency, and the same waveform. Therefore, the basic condition for interference to take place is phase coherence. Now, I have given a summary at the end of this lecture from wave-particle debate of Newton versus Huygens to Young's double-slit experiment, de Broglie's hypothesis, to the development of wave mechanics in 1929. Therefore, kindly watch the video till the end. Now, according to principle of superposition, when two or more than two waves pass through a region in space at the same time, the net displacement is equal to the algebraic or the vector sum of the individual displacements. This will be more elaborated in the next slides. Now, in our next slide, I will show you some examples of interference effects from daily life, and moreover, we will also discuss in detail principle of superposition, constructive and destructive interference, path difference and phase difference, then interference pattern, and I will also show you some experimental arrangements used for interference effects to take place by famous scientists from the history. Halos of light around street lamps or the moon on a foggy night, light and dark bands of light. If you look through fabricated bright source of light, these show bubbles, and these glorious colors do not come from the pigments in the wing, but arise as a result of scattering of light waves from different points on the wing, meet in our eyes and combine to give rise to interference. So all these are examples of interference from daily life. As I have stated earlier, we will study under this topic principle of superposition, constructive and destructive interference, path difference and phase difference, interference patterns, and I have also included some experimental arrangements used by different scientists from history to observe interference pattern. Principle of superposition. According to the principle of superposition, when two or more than two waves pass through a region in space at the same time, the net displacement is equal to the algebraic or the vector sum of the individual displacements. So these two waves, red and green, their superposition will give rise to this resultant, this purple color. Considering 2-3 points here, like for example, at this point, green and red both have the same displacement, 3. Their algebraic sum give rise to 3 plus 3 equal to 6. At this point, green has minus 2.7 and red has minus 4. Minus sign indicates that these points lie along minus y-axis. Their resultant gives the algebraic sum minus 2.7 plus minus 4 minus 6.7, this one. Again, this point is at minus 0.9 and this one minus 2.1. Their algebraic sum gives minus 3. So resultant is this one. Now these two diagrams show constructive and destructive interference. Waves that combine in phase add up to give bright fringes. This is called constructive interference and sources are said to be coherent. In this case, see, this crest overlaps with crest. So path difference is 0. So constructive interference will take place and we will get bright spot. Here in this case, crest lies over trough. So destructive interference will take place and we will get dark band or dark spot. Waves that combine 180 degree out of phase. These two are 180 degree out of phase or lambda by 2 path difference. So when waves combine 180 degree out of phase, they cancel out each other and yield dark fringes. They are coherent still as the sources have a constant phase difference, the same frequency and the same waveform. Again, I have drawn this sketch for showing the constructive and destructive interference at different points from two coherent sources, of the waveforms from two coherent sources. For constructive interference, path difference is an integral multiple of wavelength, and for destructive interference, path difference is an odd multiple of wavelength. Now these dark lines show crests and lighter or thin lines show troughs. And it can be seen that when path difference is 0, like here at this point, these all red points, wherever they lie, it can be seen that their path difference between two wavefronts, it is 0. So we will get bright bands here. This is central maximum, m is equal to 0. This is first order, second order. On both sides we will get maxima and minima. Minima lies on these lines, blue points. So this crest and this crest, so path difference is 0. Here, trough from one wave and trough from another wave. They overlap, again path difference is 0. So it will be constructive interference all over there, here, all red lines. And in this case, see this blue point, one crest and one trough overlap each other. So they will interfere destructively because path difference here is lambda by 2. See, path difference between one crest and one trough is lambda by 2, and path difference between consecutive crests or between two consecutive troughs is 1 lambda. Again, this shows interference pattern, bright and dark fringes. So interference effects are observed with all types of waves like light, radio, acoustic, water, gravity, and matter waves. Now, how to differentiate between path difference and phase difference? Path difference is the extra distance traveled by one of the waves compared with the other. So in these two sinusoidal waves, the path difference is lambda by 4. And phase difference between these two waves is pi minus pi by 2, pi by 2, which is 90 degree, because pi is 180 degree. Now here we observe interference pattern. There are different types of experimental setup to view or observe interference fringes. For example, this is another experimental setup, Michelson interferometer. Newton rings are also examples of interference fringes, but here you may see that only experimental arrangement is different. So this is just a magnified view of interference pattern. So these are different arrangements used by different scientists. This arrangement is known as Michelson interferometer, and these are Newton's rings. And this is the experimental setup to observe these interference patterns.